Hello guys, welcome to another video tutorial by No Statistics No Talk. In this lesson, we're going to have a look at linear correlation and regression. So here are the subtopics of today's lesson. First, we're going to discuss scatter diagram and linear correlation. The second subtopic is correlation coefficient R. The third one is linear regression, where we're going to focus on least square equation. The fourth one is making prediction, and the final one is coefficient of determination, R-square. Before we go any further, let's recap what we have learned in the previous lesson. You can check the video tutorials on chi-square test on the YouTube channel. Chi-square test has two types of tests, namely independence test and goodness of fit test, whereby the concern of the test is to check whether or not two variables or two datasets have a relationship or fit into each other. So here is the flow chart. If there is no relationship between the two variables or the two datasets, we would just end up with a conclusion saying that there is no correlation. But if there is a correlation, then the next concern is to find out how is the correlation between the two variables or the two datasets. So that brings us to today's topic, where we're going to find how to develop a correlation between two variables. Let's kick off with the first subtopic, that is scatter diagram and linear correlation. So what is scatter diagram? By definition, it is a mathematical diagram that graphs pairs of numerical data with one variable on each axis in order to look for a relationship between them. If the variables are correlated, the points will fall along a line or curve. The better the correlation, the tighter the points will hug the line. So here are examples of two scatter diagrams. In both examples, you can see that there are several points plotted or scattered. So that's why it is called scatter diagram. Basically, when we plot the data points, we would like to see how the y variable change with the x variable, or how is the correlation or relationship between them. Y is known as dependent variable, whereas x is known as independent variable. The reason why they are named so is because Y represents response, or things that we normally measure in an experiment, whereas X represents a parameter that doesn't depend on the response, or Y. For example, time. Let's say we want to measure the change of bacterial cell concentration over time. So obviously, when we ferment the bacteria, the cell concentration will increase from time to time. For example, the cell concentration at 5th hour is more than it is at 2nd hour, and so on. But if we have a look at time, it doesn't depend on the cell concentration. No matter how much the concentration has increased, the time will just go on. So that's why it is called independent. It doesn't depend on other variables. So that perhaps illustrates what are dependent and independent variables. In the first example here, you can see that the y is proportional to x. As the x values increase, the y values also increase. Or you can also say that both are moving in the same direction. In the second example, the trend is opposite. As x increases, you can see y values decreases. So we can say that the two variables are inversely proportional. So these are examples of scatter diagram. In short, you can say that it comprises of scattered points throughout the graph. So now let's move on to linear regression. Once we have a scatter diagram, we need to analyze the trend of the relationship between the two variables. This can be done by correlation analysis. Basically, It is an analysis to measure the strength or closeness of the relationship between the two variables. So how to do the analysis? It can be done by establishing what we call best fitting line, which can be formulated mathematically using the method of least squares criterion. The equation is in linear form with a standard equation format of y equal to a plus bx, where a is y-intercept and b is the slope. We're going to have a look at how to solve for a and b values in the later slides. Suppose we have this scatter diagram. So the best fit line should be like this, where we can see that it covers all the data points in the graph. So that's how the name best fit line is derived. Once you have plotted a scatter diagram, it's very important for you to analyze the significant trend of the graph, because that will actually tell you how is the relationship between the two variables. So the next part here is to analyze different types of linear correlation. Let's have a look at the first example here. You can see that the scattered points in this graph do not show any specific trend, neither increasing nor decreasing. So what we can conclude for this case, there is no linear correlation between diameter and height. Now let's have a look at these four examples labeled as A to D. Let's focus on A and C first. Both diagrams of A and C show a proportional trend, or also known as positive correlation. But the difference between A and C is that some of the points of graph A are a bit far from the line, whereas in graph C, you can see that all the points lie perfectly on the line, indicating that the correlation of graph C is a perfect linear. Whereas for A, we can conclude that the correlation as a moderate linear. The same thing can be said for graph B and D, except for those two graphs, they show an inversely proportional relationship or negative correlation. So these are all the types of linear correlation that we need to know, from no correlation, positive correlation, negative correlation, and the strength of the linear correlation, whether moderate or perfect. The second subtopic that we're going to discuss is correlation coefficient, or simply known as R. What is a correlation coefficient? It is a numerical measurement that assesses the strength of a linear relationship between two variables. The values of R is between -1 and 1. Given a data set of x and y, you can solve the R value using this formula. So how the R value is associated with the linear correlation? Suppose we have these two graphs, whereby the first one here on the left is a positive linear correlation and the second one is a negative linear correlation. So the R values for these graphs is 1 for the positive linear correlation and -1 for the negative linear correlation. The closer R value is to 1 or -1, the better the line describes the relationship between the two variables. In this case, both are perfect linear correlation, so you can see that the points lie perfectly on the line, so that's why the values of R are 1 and -1 respectively. In the case where the data has no linear correlation, like in this graph, the R value is 0. The next subtopic that we're going to have a look at is linear regression, and we're going to see how we're going to create the linear regression using least square equation. Here we come to the point where we develop the best fitting equation for a scatter diagram. This is covered under regression analysis. So what is regression analysis? It is a set of statistical processes for estimating the relationships between a dependent variable and one or more independent variable. The most common regression analysis is linear regression. Actually, there are many types of regression, but here we just focus on linear regression. And in this lesson, the method that we will focus on is least square method. Least square method is used to estimate unknown parameters in a linear regression model. The notation for the least square line is given as y equal to a plus bx, where a is the y-intercept and b is the slope. I've mentioned about this standard equation in the earlier slide, if you still remember. Given a data set of x and y, you will be able to solve the values of a and b using these formulas. So now we refer the best fit line as the least square line because we use the least square method to solve the linear equation. Now let's move on to the fourth subtopic, that is making prediction. In regression analysis, an estimated or predicted equation is developed to describe the pattern or functional nature of the relationship that exists between the variables. So previously we have discussed how to develop the least square equation using the least square method that represents the behavior or the relationship of the two variables in a scatter diagram. Apart from that, one of the main applications of the equation or the linear regression is for making prediction. There are two types of prediction, namely interpolation and extrapolation. So what is interpolation and what is extrapolation? Interpolation is defined as prediction of y values for x values that are between the observed x values in the dataset. For example, the least square equation shown in this slide is established using a dataset of x value from 5 to 35. Let's say we want to predict the y value when x is between this range, apart from the points that are on the scatter diagram. Let's say when x is equal to 15, we can just use the developed equation. Once we know what is a and b, we plug in the value of x equal to 15 and we will get the corresponding or the predicted y value. So that is what we call interpolation. But what happens if we want to predict the y value when the x value is not between 5 and 35? Let's say when x is equal to 40 or when x is equal to 2, that is less than 5. So this kind of prediction is called extrapolation, which means that the y values is predicted for x values that are beyond or outside the observed x values in the dataset. There are some important facts of prediction. First, the least square line may or may not reflect the relationship between x and y for values of x outside the data range. So for interpolation, it is not a problem, but for extrapolation, the prediction may or may not be true. Secondly, the least square line is based on a sample data, and each different sample will produce a slightly different equation. And lastly, the model or equation can only be used to predict the y values because the least square line is developed with the x as the explanatory variable and y as the response variable. So means that we have to predict the values of y when x is known as so and so, and not the other way around. This is because we know that x is an independent variable and y is a dependent variable. The final subtopic in this lesson is coefficient of determination, or known as R-square. Coefficient determination, or R-square, is a measure of the proportion of variation in y that is explained by the regression line using x as the explanatory variable. Suppose we have this scatter diagram and the least square line. Since this is not a perfect linear correlation, you can see that there is a deviation between the actual points and the point on the least square equation. There are two types of deviation, namely unexplained deviation and explained deviation. The unexplained deviation refers to the difference between the point that is above the line and the point on the least square line, whereas the explained deviation refers to the difference between the point that is below the line and the point on the least square line. The R-square value is defined as the ratio of explained variation to the total variation. Recall in the slide before, we have discussed coefficient of correlation, or R. So the R-square value can be determined by squaring the R value determined using the above formula. So that's the end of the 5 subtopics in this lesson. Let's recap. The first subtopic is about scatter diagram and correlation analysis. The second one is on correlation coefficient, or R. The third subtopic is on linear regression and least square equation. The fourth one is on making prediction. And the final one is on coefficient of determination, or R-square. Thank you very much everyone for joining today's class. Stay tuned to our next video tutorial on how to solve problems related to today's lesson. Please subscribe to No Statistics No Talk on YouTube for more video tutorials on statistics.